Welcome, welcome to the deep dive. We have a highly focused mission for you today.
We really do.
Yeah, we are unpacking the Class 15 notes from CS330, Programming Languages and Compilers. And this is basically the final epic boss battle of the C language portion of the course.
It's definitely a major turning point in the material.
Right. And to make sure we cover all the angles, we're pulling directly from the detailed lecture slides and also checking the course syllabus for some administrative context.
Which is good because it's an incredibly dense set of material. We're looking at C structures, unions, and dynamic memory allocation.
The big three.
Exactly. These are the tools that pull you away from simple single variable programming and they force you to manage the physical reality of the machine's memory.
And there is an immediate, highly practical reason you need to understand this. You have a lab assignment due this Wednesday where you are expected to apply these exact concepts to build a linked list and a binary tree from scratch.
No pressure, right?
Yeah, no pressure at all. But our goal today isn't just theory. It's to arm you with the exact knowledge you need to crush that upcoming lab, to bridge that gap between the theory in these slides and the actual code you are going to write.
I'm really glad we're doing this. It's a significant shift in how you write software. When you understand how to manually organize data and claim space on the heap, you stop relying on the compiler to do the heavy lifting. You take control. It's really the ultimate shortcut to understanding how computers actually think about data.
I totally agree. I see you've got your notes ready. And honestly, thinking about memory blocks, I'm just picturing a digital cityscape where all the buildings are just sequential blocks of computer memory.
That's a great way to visualize it, actually.
Okay, let's unpack this, starting with C structures.
Yeah.
Up until this point in the course, we've mostly looked at isolated variables. You declare an integer, maybe a character array.
Right, very basic stuff.
But a structure, or a struct, allows you to create a custom data type by bundling related variables together. The classic analogy is an employee contact card. You wouldn't want an employee's name, their ID number, and their office location floating around as completely disconnected variables in your program.
No, that would be a nightmare to keep track of.
Exactly. A struct lets you package them into a single logical unit.
The visual way to think about this is drawing a boundary around related data. The slides use a really great foundational example from 2D geometry.
Oh, or the points and rectangle.
Yeah. They define a custom type called a point using the struct keyword. And inside that boundary, inside the curly braces, they place two integers, an x coordinate and a y coordinate.
So just struct point and then in x and in y inside.
You got it. Once you define that blueprint, you can declare as many point variables as you want, and each one will carry its own paired x and y values.
But let me ask you about the physical reality of doing that. If I'm bundling all this data into a custom type, let's say a complex struct with a dozen different integers and strings, am I introducing a massive amount of overhead just by wrapping it in this structural package?
Oh, I see what you mean.
Yeah, it seems like creating a custom container would slow things down.
That is a very common misconception, actually. A struct isn't an object in the Java or Python sense.
Okay, so no hidden features.
Right, there is no hidden metadata, no method tables, no inherent overhead. Structs are basically classes with public attributes, but absolutely no methods. To the compiler, a struct is just a set of instructions about how to lay out data sequentially in memory.
I see.
When you define a point with two integers, the computer simply reserves the exact amount of space needed for two consecutive integers. It's a logical grouping for the programmer, not a heavy computational wrapper.
That makes a lot of sense. And the notes show how you can build on that logical grouping hierarchically. Once you have a point struct, you can use it to build a rectangle struct.
Yes, the maker-ect example.
Right. Instead of holding raw integers, the rectangle struct just holds 2 point structs, one representing the upper left corner and one for the lower right corner.
And this is where we see the concept of data encapsulation taking shape in C.
Yeah.
You aren't just passing around 4 random numbers anymore. You are passing around a concept.
Which is so much easier to read.
Exactly. The slides illustrate this with helper functions like tinrect, which is a function to check if a specific point falls within the boundaries of a given rectangle. The function signature just takes a point and a rectangle. It's clean, it's readable, and it conceptually maps to the real world.
So what does this all mean when we actually start moving these structures around in our program? Let's say I have a massive struct, maybe a database record with hundreds of fields.
Okay.
If I pass that struct into a function, is the compiler implicitly optimizing that transfer in the background to save memory?
Absolutely not. And assuming that it does is a trap that catches a lot of developers. Yes. In C, by default, parameters are passed by value. That means the compiler takes your massive database record and makes a full, heavy, byte-for-byte copy of it just to hand it to the function.
Oh, wow.
Yeah, if you pass that struct to 5 different functions, you are copying all of that data 5 times. You will quickly exhaust your available memory and completely cripple your program's performance.
Right. The computer does exactly what you tell it to do, even if it's incredibly inefficient. Yeah. So to solve this, the slides introduce pointers to structures.
The ultimate efficiency game.
Exactly. Instead of handing the function a massive copy of the data, we just hand the function a memory address. We tell the function, the original data is over here at this address, go look at it.
Right. And to trace the syntax from the slides, you declare a struct, let's say struct point P. Yeah. Then you grab its address with the ampersand symbol, so NP.
Yep.
And then you declare a pointer to hold that address, like P2.
Got it. But doing that manually, like actually accessing the data inside the struct once you have the pointer, is visually terrible.
It really is.
You have to use parentheses to force the compiler to dereference the pointer first, and then use a dot to grab the internal variable, like p2.x.
You really have to watch your precedents there.
Yeah. There's a lot of visual clutter, and if you forget the parentheses, the compiler tries to apply the dot operator to the memory address itself, which throws a massive error.
Precisely. What's fascinating here is how C gives us a shortcut to access members of a struct via a pointer to avoid that exact headache.
The arrow operator.
Yes. Instead of writing out that clunky dereference, you just use a dash and a greater than sign, literally drawing an arrow pointing to the variable you want, so P2x.
Haha. It saves so much typing. It instantly dereferences the pointer and grabs the member in one clean step.
It is the professional standard, and it is exactly what you will be expected to use in your lab work.
Okay, so pointers solve the problem of moving data around efficiently, assuming the data already exists somewhere in memory.
Yeah.
But what happens when we don't even know how much data we are going to need until the program is actually running and interacting with the user?
That is the big question.
Because up until now, we've relied entirely on C to manage memory automatically via stack variables. You declare a variable, and the compiler sets aside space for it automatically.
If we connect this to the bigger picture, this is the defining challenge of manual memory management. In modern languages like Java or Python, the new keyword handles this invisibly.
Right, you don't even think about it.
Exactly. But if you are building an application in C where a user can upload a file, you don't know if that file is 10 kilobytes or 10 megabytes. The stack requires you to know the size of your variables at compile time.
So we have to escape the stack.
Yes. To escape that limitation, we have to request memory manually from a different region of the computer called the heap.
And the tool for that is malloc, short for memory allocation. The notes are very specific about how this mechanics works. You call malloc and you pass it the exact number of bytes you need.
Though you shouldn't hard-code those bytes.
Right, because an integer might be 4 bytes on one machine and 8 on another. Mm-hmm. So you use the size of operator to let the compiler calculate it for you.
Spot on. And because malloc is just grabbing raw, generic bytes from the heap, it returns a pointer to the very first byte of that space. It essentially says, here is a memory address where your raw data starts.
Just a completely generic pointer.
Exactly. So for type safety and clarity, it is up to you, the programmer, to cast that generic pointer into something useful, like the slides arrays or the phoneme struct examples. You have to explicitly tell the compiler, treat this generic block as a pointer to an integer, so cast it to int.
I want to pause here because there is a massive conceptual hurdle that isn't always obvious until your code crashes. What happens if I ask malloc for a gigabyte of memory, but the system is out of memory? If malloc fails, what does it actually give me back?
This is one of the most critical points in C programming.
Yeah.
If malloc cannot fulfill your request, it does not throw a convenient exception. It quietly returns a NUL pointer with a value of 0.
And if I assume the allocation worked and I try to write data into memory address 0,
you trigger a segmentation fault, and your program is immediately terminated. Fatal crash. Every single time you call malloc, your very next line of code must be an explicit check to see if the return pointer is NULL.
So if you skip this step in your Wednesday lab, you are leaving a ticking time bomb in your code.
Exactly.
Well, here's where it gets really interesting, because even if malloc succeeds, your responsibility is just beginning. C has no garbage collection.
That is the trade-off for having complete control. When an automatically allocated local variable on the stack goes out of scope, it's cleaned up automatically.
Or heap memory.
It just sits there, unavailable forever. That memory is yours until you explicitly give it back.
So if I allocate memory inside a function, and I don't give it back before that function ends, the local pointer variable I was using to keep track of that memory just disappears. The memory is still checked out, but I no longer have the address to find it.
You've created a memory leak, and the consequences compound quickly. You will consume all the available memory on the machine, causing programs to crash, lose data, and create very unhappy users.
The lecture slides offer a very strict mantra to prevent this. Finish what you start.
Finish what you start. It's the golden rule.
If a specific module allocates memory, it is generally responsible for freeing that memory when it is done using the free function.
But again, you have to be meticulous. If you try to free a pointer that you've already freed, you will cause a crash just as severe as a memory leak.
It requires intense discipline, which brings us to a fascinating structural problem. If memory management requires this much discipline, how do we build complex structures that need to grow indefinitely?
Right, like the data structures in the lab.
Yeah. The slides introduce self-referential structures. Now, a structure fundamentally cannot contain an instance of itself. That makes sense. It would require infinite space. But a structure can contain a pointer to its own type.
This is a brilliant workaround. Let's look at the struct node example from the notes. Inside this struct, you have a variable holding your actual data, say, a char value. But right below it, you declare a struct node next, a pointer that holds the memory address of another node.
This is how we build a linked list.
Exactly.
Instead of allocating a massive array all at once, we just malloc one single node. When we need another piece of data, we malloc a second node, and we make the first node's pointer point to the address of the second node. We chain them together.
And that struct node pattern is the exact blueprint you will need to pull this off successfully for your homework.
Oh, absolutely. So, to you listening, remember your lab assignment this Wednesday is to apply these exact concepts: self-referential structures and dynamic memory allocation with malloc and free.
And for the binary tree portion of your lab, you apply that exact same logic. But instead of one pointer pointing to the next node, your struct will have two pointers, a left pointer and a right pointer.
Building data structures that can branch out and grow dynamically. Just remember to traverse that entire tree and free every single node when you are done.
Don't forget that step.
Now, we've talked extensively about grabbing memory and chaining it together. But there's another tool in Class 15 that is entirely focused on conserving memory unions.
P's poor polymorphism.
Yeah. Structurally, a union looks identical to a struct. It uses curly braces, it has member variables, but beneath the surface, the memory layout is entirely different.
It really is a massive twist. In a standard structure, every member gets its own space. In a union, all the variables share the exact same memory location.
Okay, so what's the catch? Let's use the union number example from the slides, which has an int I and a float f. If I assign a value to I and then assign a value to f,
You completely clobbered the integer value. The bits are overwritten. You can only use one member at a time.
this raises an important question. Why would anyone use this if it's so dangerous?
Well, it provides a workable, as we said, poor approximation of polymorphism. It saves memory when you have mutually exclusive data.
Like what?
Think of a vet's database. A patient doesn't need both mammal and reptile data simultaneously. A union lets the same block of memory hold either type, cutting your memory footprint down.
Oh, okay. And the syllabus notes make it clear that this concept is going to be vital for the compiler you are building in this course, specifically for abstract syntax tree or AST nodes, where Elixir assigns values based on the specific token type.
Right. The token might be an integer or a string, but never both at once. A union is the perfect memory-efficient container for that.
That makes total sense. So let's do a quick recap of the tools you've just acquired. You have structs for grouping data logically,
Pointers for moving it efficiently,
malloc and free for manual memory control on the heap,
self-referential structs for complex, growing data.
and unions for memory-saving polymorphism. You are now fully prepped to code those linked lists and binary trees for your Wednesday lab. And just a casual reminder from the syllabus Lab 5 is fully due by Sunday.
Good luck with that.
Yeah.
I want to leave you with a final thought to mull over. When you program in modern languages like Python, the computer hides the physical reality of the hardware from you.
Yeah, completely.
But C forces you to manually manage every single byte. How does intimately controlling the creation and destruction of memory change the way you fundamentally design your software?
A great question to take into the lab. Thanks for diving in with us today. We'll catch you on the next one.